All right, what up, everybody? Today we're going to be talking about standing waves and the patterns that you'd see as you get different harmonics in a standing wave. So, the picture on the screen is a string that is exactly 1 meter long, and somebody's shaking it at such a frequency that you'll see we have one, two, three, four, five, six bumps, right? Um, and as we've discussed before, if you were to shake it slower, you get to five bumps. If you shake it even slower, you get four bumps, and so on. Right. So it depends on the frequency that you're shaking the string. Right. And keep in mind that the string here, the crest here, that part of the wave is going to go down and become a trough, and it's going to back up. Same thing here. This trough is going to go up and become a crest, then go back down. So the string is moving, but this is what it would look like if you just took a still picture of it. All right, so first of all, what harmonic number is it? This is a sixth harmonic, and to find that, you just have to count the bumps. So one, two, three, four, five, six. How many waves are there? Keep in mind, a wave, to be a wave, you have to have a complete cycle. So you need a crest and a trough to make up one wavelength. So each bump is not its own wave. Each bump is actually half a wave. To find how many waves, you would have to take the number of bumps and then divide by two. Okay, so there's six bumps, which means you have three waves. Six divided by two is three. So you can kind of picture if you start from the beginning, it goes up, down, then up again. That's the beginning of the first wave. So the first wave stops right here. Goes up, down, and up again. That's the end of the second wave, and then it goes up, down, and up again. There's the third wave. Okay, now what's a wavelength, right? How long is each wave? Well, there's three waves, and they're on a 1 meter string. So we just take the length of a string and divide by the number of waves. Okay, so in this case, it's a 1 meter string and there's three waves, so we'd have 0.33 meters. So you're just going to take the length, again, just the length of the string and divide by the number of waves. Okay, nodes. Nodes are those areas that are touching the middle line here. And there are going to be, in this case, we have one, two, three, four, five, six, and there's also a seventh here, but we don't have a dot for some reason. Um, but it's always going to be one more than the harmonic number. So this is a sixth harmonic. You expect seven nodes, right? If it was the first harmonic, you'd have two nodes. If it was the 88th harmonic, you'd have 89 nodes. So it's always going to be one more node than um, the harmonic number, as long as you're talking about a wave on a string where both sides of the string are being held down. Okay, antinodes are the parts in the middle of each bump, which go all the way from the top down to the bottom and up to the top again. So they're the parts that move the most. And each bump has one, which means that if the sixth harmonic would have six antinodes, because the sixth harmonic has six bumps. All right, the harmonic number, and the number of antinodes will always be the same for any string that's being held on each end. Okay, frequency. All right, let's say that we're told that this wave right here has a frequency of 24 hertz. Okay, which means that if you look at the top of each wave is going to go down to the bottom and up again, um, 24 times each second. Okay, and it asks us what's the velocity of the wave. So how do we figure out that? Well, there is an equation. Okay, and the equation says that the velocity is equal to the wavelength times frequency. Right, so we just need to know the wavelength and frequency. Now, before we figure out what it is, let's talk about what does it mean. What velocity are they talking about? It's not talking about the velocity of the string going up and down. What it's talking about is how fast energy is going from one side of a string to another. So, like if you were holding this string and you flipped your wrist and caused a little wave to go down the string, that wave would move away from your hand at the wave speed, whatever this velocity is, and then it would bounce off the other side and come back at that velocity. So that's what we're talking about with the velocity. So we found out that the wavelengths was 0.33, right? That's because there's a 1 meter string and there's three waves. So we did one divided by three. And we're told that the frequency is 24 hertz. That means that 0.33 times 24 will tell us the velocity. and the velocity would be 8 meters per second. Okay. Next, let's talk about how to go from one harmonic to another. Okay. So harmonics are special frequencies at which um, distinct bumps will develop in a string that's being vibrated back and forth. So if you're not on harmonic, you're still going to see the string go up and down, but the crests and the troughs are not going to stay in the same place. They're going to look like they're going to go side to side. They're going to move side to side across the string. But if you're at a harmonic frequency, the crests and troughs stay in the same place and they just vibrate up and down. So you have places where it's going up and down, and you have places where it's not moving at all, right, except for rotating back and forth. Okay, so the harmonics happen in equal increments, okay, which means if the frequency of this harmonic is 24, and this is the third harmonic, we have 3 bumps, then you can divide that by 3 to find what the first harmonic would be. Right, so 24 divided by 3 is 8. So if we take this string and we slowed down the vibrations to got to 8 hertz instead of 24, then instead of seeing 3 different bumps, you would see 1 bump that moved up and down. Okay, and to find the second the harmonic, you would take the harmonic of the first one and multiply by 2. Okay, and if you want to find the fourth, you multiply by 4. If you want to find the fifth, you multiply by 5. So you can find any harmonic now that we know the first harmonic. Okay, so if we shook the string at 16 hertz, then you'd see 2 bumps. Okay, so now let's see if we can recognize patterns as we're going from one harmonic to another. Um, the first harmonic happens at a certain frequency, then you double that frequency, you get the second. If you triple the first frequency, you get the third, and if you quadruple the first frequency, you get the fourth. All right, we're going to fill out this chart, and the first thing it wants is the number of nodes. And so the number of nodes is just how many places does the wave get stay in the middle. So put a blue dot on the nodes, and we can count them. We see that the first harmonic has 2, the second harmonic has 3, the third harmonic has 4, and the fourth harmonic has 5. Right. So as you can guess, the pattern is that there's one more node than the harmonic number. Okay, so you take the harmonic number plus 1. We'll give you the number of nodes. Antinodes. Notice each bump has an antinode. So the first harmonic is 1 bump. It would have 1 antinode. The third harmonic is 3 bumps, has 3 antinodes, and so forth. So the number of antinodes is always equal to the number of harmonics on this type of wave. Okay, wavelength. All right, so this takes a little more thinking. A wavelength is how wide 2 bumps are, because 2 bumps make up a wave, right? Because a wave needs to have a crest and a trough, which takes 2 bumps. So for the first harmonic, all right, and let's pretend like this is a 1 meter long string, just to make things easier. The first harmonic is just 1 bump, so that's only half a wavelength. And if half a wavelength was 1 meter, you need another meter to make the other half. So the wavelength would be 2, right? For the second harmonic, there's 2 bumps, okay, and 2 bumps make up 1 wave, which means the length of the wavelength would just be 1 meter, because the string is 1 meter. The third harmonic only takes up 2 out of 3 bumps, so the wavelength would be 2/3 of the length of the string, and the length of the string is 1, so the wavelength would just be 2/3. And the fourth harmonic, the wavelength takes up 2/4 of the string, so that would be 2/4 meters long, or 1/2. So there you can see the pattern for wavelength. Basically, to find the wavelength, you're taking it's 2 divided by the harmonic number, right? And so 2 divided by 1 is 2, 2 divided by 2 is 1, 2 divided by 3 is 2/3, 2 divided by 4 is 2/4. If the string was not 1 meter, if it was another length, let's say 3 meters, then you would just multiply these numbers by the length of the string and you would get the wavelength, right? So for instance, if it was the first harmonic and it was a 3 meter long string, then you just do 2 times 3. Okay, so now let's talk about frequency. Okay, the frequency of the first harmonic is 4. Okay, we're given that information, right? And that's something you can find out using an experiment, or someone can just give you the information. To find the harmonic, the second harmonic, you'd have to do that harmonic times 2, 4 times 2, then 4 times 3, 4 times 4, and you can easily get the frequencies that way. Finally, we want to find the velocity of the waves, and the velocity is equal to wavelength times frequency. So you see in each row we have a wavelength and frequency. We're just going to multiply those two numbers together, and we get 8 for each of the harmonics. So surprisingly, uh, we go through the harmonics, we still get the same velocity, right? Because remember, to go from one harmonic to another, you have to shake the string at different frequencies. Like if you go from the first harmonic to the second harmonic, you have to double how fast you're shaking the string. That actually does not affect how fast the energy moves through the string, so it doesn't affect the velocity, right? Whether it's the first harmonic or the 100th harmonic, the velocity at which the energy goes from one side of the string to the other would stay the same. In this case, 8 meters per second. Okay, hopefully this answers your questions about standing waves, and I'll see you all in the next video.